Okay. Yeah. So number 6 in the lab or number 6 in the homework? Let me load it. This is the machine language homework or the first homework? So the first homework, so this is the one that was due Tuesday, right? So I thought I talked about this last time. Um, what I'm asking for is if I have a memory system where so if you think of this like the chart that you had for the D machine, where you have a giant table of memory. If I have 6 billion slots, and I want to give every slot a number 0, number 1, number 2, number 3, number 4, all the way down to slot 6 billion. How many bits do I need to store all 6 billion different location numbers, all 6 billion different address numbers? So all it's really asking is how many bits do I need to count up to 6 billion? So I'm not sure what else you want me to say about that. Okay, cool. All right, any other questions on any of the homeworks? What I'm going to do, I haven't graded the first homework yet, but I'm going to try to grade it the next day or two and send you out my corrections or whatever's, and I'm also going to send you out my answers to all the questions so you can see kind of how I did them and stuff like that, so you can look at it. So expect that in the next few days um, to help you understand these homeworks. So that will be coming. Any questions on the machine language stuff or the lab? Like I told you to look at. I tried to do the lab after I clicked run compile. It just stayed on one window. That so like this other window didn't pop up is what you're telling me, the blue one. Um, did you may have gotten a Java warning? I don't know if you can see my screen. We probably can't. Like at the top part of your screen, you may have gotten some kind of Java. I bet what's happening is either your machine's not running Java right, or it's not, or it's blocking the. Yeah. That's weird. So why would you not? Sometimes I have to like so if I have the thing open, um, I don't know what I just did. So if I have the thing open and then I close it by Xing out of it, and then I go back to how come I can't share? Okay, and then I go back to the loading screen. This is the screen you're talking about, right? If I go back to the loading screen, it won't load again, even if I hit regular reload. It may or may not load again. I get this white box. So what I usually have to do is, well, hey, but it shows up and it shows up all yucky. Is close the whole window up and then restart a new tab, or even just restart the whole browser, and then go there. And sometimes this will work just from kind of restarting everything. So we'll see if this works. Yeah. And then I get it. So I guess what I would say is try. Until Java just still no. I wonder if you have some kind of pop-up blocker running that it's automatically stopping everything from popping up. I wonder what happens if you. Whoops. if you go back to the other page, this is the original page, and hit download instead of run. Let's see what this does. And now I get something in the download. Oh, you don't want to do that. Ugh. There's a way to do this, but I think you're not going to like it. Are you a Mac person or a PC person? If you have Safari, you're a Mac person. So yeah, okay. Let me see if this horrible idea I'm about to tell you about actually works. And then Java. What do I want to use here? Let's try compiler Applet. I'm not sure what the right thing to run here is. All right, so this is not the easiest thing in the world to follow. So let me see if I can explain this remotely. Keep clicking the Java icon. But you had a Java icon to click. Do you get so when you go to download, do you get a white box in here, or do you get run the compiler? Do you get a white box in here, or do you get like a Java icon in there? See, now I get nothing. But now I get a white box, which I think means it's trying to run it. And then hopefully in a second it'll run. And if I double click this box, I don't know. All right. So here's my horrible idea. This may or may not work. So you go back to the original page, and instead of hitting run the compiler, you hit download the compiler. What this is going to do is download and save it to your hard drive. Saying save file is probably okay. All right. Then, down at the bottom of your screen, there's going to be, that's weird, there's going to be an application called the terminal. And if you run the terminal, I'll show you what my terminal looks like. I will try to show you what my terminal looks like. Where is it? There. You get a window that looks like this with a bunch of words in it. Yours probably will look like this when you start it up. So you'll probably end up having a prompt that looks something like this. Can you see that? Yeah. Okay. So this is a text-based finder basically, where you get around by typing stuff instead of by clicking stuff. So the command to go into a folder is cd, and so you would say cd downloads, and spell it right. And then you guys can still hear me, right? The thing just told me my microphone is muted. You guys can still hear me, right? Okay, good. I don't know, I got this weird message. And then you do cd into, I think it's called Brookshire Machine is the name of the thing you downloaded. And then you gotta type Java compiler. And then this is gonna run the compiler from your hard drive and hopefully avoid all of the crappy security stuff. So I don't know if this is better or worse, but and there it is. I don't know if this is better or worse, but at least it's something if it doesn't run. But if you need help with that, it's probably better for me to explain it to you kind of separately. But if you tell me it worked in Firefox but not in Safari, I'm glad it worked for you in something, I guess. Yay. So you got it at least working a little, right? All right, cool. All right, any other questions about how this is working and what this is doing? Those of you that got it running, did you get at least through the first part of the lab with the basic programs and stuff like that? Okay. So you guys are more or less comfortable with the ideas. So homework 2, yeah, that's fine. Or just send them in a Word document, send them an email. All I want is the codes. Having English words explaining what you're doing will help me understand the programs, because even I have trouble reading random hexadecimal digits. So, but yeah, the thing you need to hand in is if you export the program, it'll give you kind of a thing you can copy and paste from, and then you just take that and copy it into an email message or a Word document or whatever. Yeah. Okay. All right. So the big ideas that you ought to have at this point are programs are written in machine language. 2, that machine language is written as binary or hexadecimal numbers, and that's why you have all those weird digits in your programs. And 3, programs sit in memory. Whoa, what did I just do? The program counter holds the location of the next instruction to run. And I guess the other thing is inside the processor, registers are special memory locations that are used by most instructions. All right, so that's kind of where I want you to be right now, plus a little bit of having a basic idea of being able to at least follow a couple of those different instructions. Instruction 2 to load a register, instruction 5 to add 2 numbers, that sort of stuff. So this is where I want to make sure we're all at. So if you have questions on this stuff, ask. Stop me now. All right, so let me bring up, I think I lost it. Let me bring up that applet again. So I want to show you, I want to walk you through this in like a real program and show you how it works. And there's a couple of things I want to make sure we all can see as we go. So here is the machine. I need to make sure you can see the machine. And I need to share this guy. All right. So here's the world's smallest program that does something kind of useful. So the first instruction is 20001. I'm gonna 2001. I don't know why I can't fit all 4 digits in the thing here, but oh well. The second instruction is 2102. So what 2001 does is put here. Well, here's the simplest program. So if I run through this, 2001 puts a 1 in register 0. 2102 puts a 2 in register 1. And then what I'm going to do is 5312, which adds them and puts them in register 3, and then I'm going to stop. So what this program will do when I run, will zip through, stick a 1 in register. Oops. I put them in the wrong registers. Put a 1 in register 0, put a... Let me fix this because I added the wrong 2 registers together. All right. What this program will do when I run it now, we'll put a 1 in register 0, put a 2 in register 1, add them together, put the sum in register 3, and then I have a 3 in register 3. Yay. Okay. What I want you to notice is how the program counter here is changing as I go through the program. Okay, so before I start, the program counter is set at 0, and that's the memory address 0 of the first instruction. Okay, and then when I hit step, I step through and I do just the first instruction. That was the loading register 0 with the 0, 1, and the program counter automatically changes. I don't have to do anything. The program counter automatically changes to be now pointing to address 2 in memory, which is the next instruction. And when I step to that, I do that, and I put a 2 in register 0 in register 1, and the program counter changes again to be the location of the next instruction, and again until I stop. Okay, so every instruction. This is the fetch execute cycle that I talked about last time. Every instruction automatically changes the program counter. Okay, and so the programs that you're supposed to look at for the first half of the lab, and the programs that you're supposed to do for the first couple of homework problems, make the program counter. You don't do well. The program counter goes up automatically every time, and we do all of the instructions in the program one at a time. Okay. The second half of the lab walks you through the idea that we can, if we want, change the program counter and make it do different things. So normally the program counter goes up by itself after each instruction. And a program does all of its instructions in order. Okay. It's also possible to set the program counter to a different value based on some condition. Now the reason we'd want to do this, okay, is if you think about it from an algorithm standpoint, from a what kind of a problem am I trying to solve standpoint, it lets us ask a question and if the answer is yes, do something. And remember, doing something is just performing instructions at some location in your program. And if the answer to your question is no, we can do something else. Something. And the idea is that these are different sets of instructions that live at different parts of the program. And so we need different program counter values to do the instructions. So I haven't read the homework yet, but the first question of the homework was to write the algorithm to put on the coat, and probably you had things in there like see if, put your arm in this hole, and if your arm's in this hole, it's right. If your arm's in the other hole, it's wrong, and fix it, and stuff like that. Things where some of the steps, or at least some of the things you're supposed to do and look for, only happen sometimes. And so if you don't have the ability to change the program counter yourself, then the only way the program counter gets changed is automatically after each instruction, and therefore the only kind of program you can write is one that starts at the top and does every single line in order all the way to the bottom. So if I want to have the ability to do different kinds of things based on different situations, I need a way to change the program counter to do one way or another. Okay. The other thing we need, another thing we can do if we're changing the program counter ourselves, is do something and then figure out if we want to do it again. And if the answer is yes, we want to do it again, we go back up to do something again. And if the answer is no, we move on down. And so doing something again, doing a task repeatedly, means we need to set the program counter to point to an instruction we're past and go back and do it again. Okay? So the point is, this is why we care about setting the program counter ourselves. Okay? So the second half of the lab walks you through thinking about an instruction called instruction B. Changes the program counter sometimes. And so the idea is, if I do this, B144, what happens is, and this is just by the rules of the machine language, okay? See if register 1 equals register 0. If they have the same number inside, the same bits inside. If they do, set the program counter to 44, do that instruction next. If they don't, if they're not equal, do the next instruction below this one like normal. So the point of instruction B is to maybe do something else at a different part of the program depending on whether two numbers are equal. It's always register 0 that we compare against, and this second digit is the thing we compare against register 0 depending on the value. So, wonder if this was up the whole time. So if you haven't seen my screen because I had this stupid machine up this whole time, sorry about that. So let me share the B machine. So here's a very, very simple program. I'm going to keep what I had before. I'm going to load a 1 into register 1. I'm going to load a 2, well, a 1 into register 0, a 2 into register 1. Instead of adding, I'm going to do B1, I don't know, 18. And the text here says, if the bit pad in register 1 equals the value in register 0, jump to location 18. And what I'm going to do is do one more thing and put a 99 in register 3 if I stay here and then stop. And then down at register 18, I'm going to put a 77 in register 3 and then stop. Okay? So if I set up the two, let's do this, the two registers at the top of the program to have, let's do different values first, to have different values. So what I'm going to do when I reset and I step is I'm going to put a 4 in register 0. I'm going to put a 2 in register 1. Then I'm going to do this B instruction that says if the bit pattern in register 1 equals the value in register 0, then jump to location 18. Since they're different and they do not equal, I will not jump to location 18. And the next thing I do will be the instruction at location 6, just like normal, which puts a 99 into register 3, and then I stop. Okay? But if I start over and I set up these two registers to have the same values, okay, then what I do is I put a 2 in register 0 and I put a 2 in register 1. If they're the same, they are. I'm going to jump to 18. Notice how the program counter is the thing that changed here as I go through. Okay, so that's what's happening here as I do this jump instruction. If they're equal, I jump, and then now I put the 77 into register 3, and then I go to the instruction below that, which is instruction 1A, and then I stop. Okay, so that's the idea behind the jump instruction. It lets me do two different things based on a condition. The condition always has to check something against register 0, and it lets you do two different paths through your program based on whether two numbers are equal. The rest of the lab, I think, walks you through a program that does the over and over part of it. And so what that does is adds all the numbers between 1 and I think 10 by doing a simple add command and jumping back to the add command over and over and over again until it's done adding. So the lab walks you through these ideas, at least the second half of the lab walks you through these ideas. I just want to make sure you kind of saw me walk you through it here so that when you're doing it on your own, you're not too sad and confused. So does that make sense? At least the idea. You can certainly get arbitrarily wacky with having jumps all over your program going in, so you can have jumps inside of jumps and jumps that repeat inside of jumps that repeat and things like that. You're not going to do that for these programs. I just want you to have the idea of how you can kind of override the program counter and some basic ideas of what it's for, and that's it. I think week 4 is the week I have you doing your own programs, not in machine language, but in a graphical language where you move cats around and stuff like that, and you'll see more of this stuff. But it's much better to think about complicated programs not in machine language. Nobody actually programs in machine language because nobody likes dealing with all these numbers. There exist other languages that interpret this stuff better. But I want you to see this so you can get an idea about how the computer actually works underneath it all. All right, so any other questions on the machine language and the lab? Well, I was kind of confused with question 16's last part. Let me look up question 16. Question 16 says, okay, so let me write this program for you. This is the program that, let me go out and change let's make this big, go out and stop screen sharing my screen, and go out and start screen sharing the Brookstreet machine. So you want a program that loads what's in memory location 40 into register 1. That would be 1140. Load what's in memory location 42 into register 2, 1242. We're using instruction 1 instead of instruction 2 because I want to go out to memory and get the thing. Adds them together, sticking the result into register 3. That is 5321. Stores the sum into memory location 44. I think that is 3344. And then stops, okay? Now, to make this work, you have to actually put stuff down into memory locations 40 and 44. And so the first, I give you this chart, okay? This is ugly, okay. If, you suck. If I can actually find memory location 40, there, all right. And I put 0400 into 40, and 0, this is really painful, 0300 into 42. Then when I step through the program, when I reset and step through the program, then instruction 1 loads what's in location 40. Notice how I get just the 04 part and not the 00 after it, okay? That's going to be important for the question you actually asked. And then I put the 03 and not the 00s after it into register 2, register 1, and then I add them. 4 plus 3 is 7. And then I stick what's in register 7 down at 44, and then I could put my 7 down there, and there it is, okay? So the last one of these said, what happens if I put this is the worst thing to type in ever. One, come on, man. Why won't you let me erase you? told you that I hate computers. 1011, and I feel like I put in way too much stuff there. Yeah, and then I don't know why. Whenever I click inside a memory location, it jumps me up to like a very different part of the program. That sucks. 1020. Okay, so these are the two things that I'm putting inside the memory address 40, memory address 42. And then when I reset and I step to the exact same program, notice how register 1 loads the 10 part just, and the second instruction loads the 10 part out of 42 just, and not the 11, and not the 11, and not the 20 that comes after it. And then when I add them and stick them out here, I get 20. Arg. Or I would get 20 if you could actually see it. There it is. Okay, and the reason for that is when I type in 1011 at register at address 40, I'm really getting two things. I'm getting the 10 placed at memory location 40, but I'm also getting the 11 placed at memory location 41. Okay, so when you type in, remember 4 hexadecimal digits is 2 bytes, right? Every hexadecimal digit is really 4 bits. 2 hexadecimal digits is really 8 bits in 1 byte. So therefore 4 hexadecimal digits is 16 bits or 2 bytes. So what's happening is they've organized this screen in going up by 2s. Okay? And it goes up by 2s means every entry you enter in here goes up by 2 bytes. This is 30 and 31. Both of those locations. If you go out to the, this is what I was trying to say, how if you go out to the memory matrix, it shows the individual bytes, but you got to read it kind of weird. So this is row 4, column 0, address 40. This is row 4, column 1, address 1. Okay. So the point of that last one was to show you that even though you're typing 4 digits into the memory location, when you load, you're only loading 2 of them. If you want the second 2, if you want the 11, then you've got to do an instruction like 2141 and get the thing out of location 41. Okay, so that's a big roundabout answer to your question, but hopefully, does that make sense? What's happening there? Okay. All right. Any other questions about the machine or the lab or anything like that? Okay. So what I want to do quickly, it's a little topic that's not big enough to make you do a whole lab or a whole homework on, but it is worth seeing and talking about just a little bit. And so since I have a little bit of time today, this seemed like a good place to fit it in, especially since we're talking about low-level machine stuff anyway. And that's talking about operating systems. So you have an idea of what they are and what they do and how they work. Okay. An operating system is a program whose job is to sit between the user and the hardware and make the hardware more usable. So one of the things that I want you to get out of the machine language is that machine language sucks. Is that trying to think in terms of machine language is hard and easily messed upable and not fun. and that we should not do it, and aren't we thankful that we don't have to do it every time we want to use a computer? And that's actually what happens. So, examples. So Windows is the operating system. Windows 10 or Windows 7 or Windows whatever is the operating system, the program that sits on your computer. Mac OS, whatever flavor you have, Eldorado or whatever the heck it is your operating system. Its job is to sit between you and the hardware and make the hardware more usable. Linux, if you've ever heard of Linux, it's a different kind of operating system that does the sitting between in a different way for you. So just like last time when I said different machines have different machine languages, and that's why they're not really compatible, another reason why machines cosmetically are not very compatible is because they have different operating systems and they do things each has different ways of doing things. The windows look different, the commands you can have look different, the interfaces to the hardware look different, but for all of them, their job is to be a program. So this is a program that is actually running on your computer right now that has machine language commands that are being interpreted on your processor right now that are doing the act of interpreting things you want to do with the actual hardware itself. So what I want to do for the last few minutes of class is to kind of zip through the main tasks of the operating system. Because it's a big, complicated program whose job is to make your computer more manageable. Okay, so one big task of the operating system is to let you run other programs. And that's what's happening when you, for example, double click to start a program. What you're doing is you're sending a command to the operating system that says, hey, here is a program that I want to start running. Can you start running it for me, please? And the operating system says, okay, what that means is I need to get the machine language instructions of this program you're trying to run loaded into memory, and I need to set the program counter of the machine to point to the first instruction of this new program, and then I need to let it go. Okay, so the operating system's job is to do all of the setup and also to let you stop running other programs. The red X. The red X is a command to the operating system, probably, that says, hey, I am done with this program, end it. And the operating system's job is to take that program's instructions out of memory, to clean up whatever data that program has used, and to make it go away and off the screen. Okay? So that's one of the things the operating system does. Another thing the operating system does is manage many programs running simultaneously on one machine. So if you think about it, right now, I don't know how to do this on a Mac, so I'm gonna look it up in 2 seconds. How I get like the task manager, which has all of the different things that are running. It's called the activity monitor. Can I find the activity monitor? Let me go look. All right. So let me share this with you on my screen. This is my activity monitor. And so what you're seeing in here is, I'm trying to get this on the recording as well. Okay. What you're seeing in here is all of the programs that are running on my computer all at the same time. Okay, so my computer is running like 20, apparently 247. That's the processes number down here. Different processes, different things, all right now, all at the same time. Now, if I have just one processor with one program counter, then somebody needs to manage running all of these guys all at the same time. And that's the job of the operating system. The job of the operating system is to basically switch the processor from pointing at all of the different programs and zipping through it really fast. So what happens is I have basically a list of web browser and my notepad program that I'm writing in and my recorder all running at the same time. They're all running right now. Right now I have the web browser that I'm chatting with you guys in. I have this notepad thing that I'm drawing in. I have the recorder that's recording this thing for YouTube, all running, and a whole bunch of other stuff, all running all at the same time. And what the operating system's doing is spending a little bit of time running the instructions of the web browser, and then after a little bit of time goes by, then stopping that, and then spending a little bit of time running the notepad, and then after a little bit of time has go by, stopping that, and then spending a little bit of time running the recording software, and then after a little bit of time has gone by, stopping that and going back around and spending a little bit of time on the web browser. And when I say a little bit of time, what I mean is like very, very small, like hundredths of a second. Okay, so hundreds of times a second, we're going to switch between running all of these different programs. And so it looks to us, because we can't see things that happen within hundreds of a second and know that they're separate activities, it's going to look to us like they're all going at the same time. In the same way that like an old, I don't know if they still make movies this way, the old film strips that are the old like giant reels of very, very slightly different pictures. And so you have a person, and then you have a person who starts to raise their hand, and then you have a person who really raises their hand. And it looks like when you show the movie that it's moving, but it's really not moving. It's just a bunch of images that are flipping by really fast, or a flip book. Have you ever seen a flip book? That kind of thing is also the operating system. It works the same way as the operating system. It looks like it's all going at the same time. It looks like the movies, the pictures are moving, but really what you're getting is a lot of single snapshots flipping by very fast. So operating system manages that. The other big thing the operating system manages is files and folders. So the idea of what a file is, instead of just a bunch of random bits sitting on your disk, is something the operating system manages. The idea of a folder as a thing that contains files is an operating system thing. That is sitting, that the operating system creates. Being able to move stuff in between folders back and forth is an operating system thing. So the point is, and then probably some also networking stuff. Managing the fact that information is being sent across the network to you from me talking, and that you are typing stuff in or talking and sending stuff over the network. The operating system is managing all of the data that comes in off of your network. The operating system is managing, deciding what that data means and what to do with it and what application to put in it. So, plus other things like security and resolving conflicts when two processes want to do the same thing at the same time and things like that. But the point is that operating systems are big, complicated programs. They are themselves programs. They do run on your processor. They do follow the same rules as all of the other programs. So like all programs, they're written in machine language. And also, like all programs, when they run, the instructions sit in memory and the program counter refers to the location of the instruction. So just because it's big and complicated doesn't mean it's not a program. And every program follows certain rules. Every program lives in memory. Every program is written in machine language. Every program interprets things as binary numbers. Every program stores their data in memory along with their instructions. And it just so happens that the operating system is a program that manages other programs and files and stuff like that, whereas like the dinky programs that we're doing for the lab are just adding two numbers or whatever. But it's just a question of scale and size, not a question of different rules. So I wanted to tell you this partially because people, I think, get confused about what's going on. So the layers of a computer. You have hardware, circuits. Those are the things that are running electronically to get your commands done. Everything in hardware is done as binary numbers, or at least binary signals. Everything in hardware is done as machine language, as circuits. That's what you have to do. This is why you have to have machine language stuff to run programs. On top of your hardware is the operating system. The operating system's job is to send things to the hardware and to know how the hardware works and to talk to the hardware so you don't have to. On top of that is what I would call application programs. So down here is where I would say I'm an Intel processor. That's what kind of hardware you're using. That's what kind of circuitry you have. That's what machine language we're running. Whoa. Let me get, I don't know what I just did there. The operating system is something like Windows or Linux or Mac OS or whatever. And that's a program that sits on top of the hardware. And when you interact with the computer, you are most of the time interacting with the operating system, who then interacts with the hardware for you. Okay? You very rarely need to talk to the circuitry directly. You talk to the operating system who talks to the circuitry. When you want to load a file, you ask the operating system to load a file. The operating system goes to the disk and reads the bits and builds it up for you. When you want to run a program, you tell the operating system to start the program. The operating system gets the bits of the machine language in there for you. And then your application programs are your, your web browsers, your games, all the stuff that you're actually using the computer for. And so that stuff is created and run and managed by the operating system. And then the operating system starts up your program, stops your programs, gives it memory, things like that, so that when the programs do their instructions and talk to the hardware, they're set up correctly. Okay? So there's a difference between saying I'm a PC and I'm a Windows machine. A PC is a hardware thing. It's an Intel processor thing. And Windows is saying what kind of operating system you're using to talk to that hardware. So that's my quick 20-minute whirlwind tour of what operating systems are and do and how they work. Obviously, there's a lot more stuff we can do. If we were in the face-to-face class, I'd probably spend a few days on it. But I do want to make sure you saw it a little bit while we had a little bit of time. So any questions on that, on operating systems, how they work, that sort of thing? Going once. Going twice. All right. Well, the lab and the homework. So what you should be doing now is working on and finishing the machine language lab and the homework that came along with it. Next week, what I'm going to do is start talking about networks and the internet. And the big lab and homework there is going to have you guys create your own web pages. So get ready for that. And I'll spend my time in here giving you the basics on that and also talking about how networks work and how communications work and that sort of stuff. Cool? Any other questions or problems or anything? If not, I will see you on Tuesday. Do ask questions about the homework. Do give yourself time to do the lab before you start the homework. This is not the kind of lab, this machine language lab, that you can kind of burn through on Monday and expect to do all the homeworks Monday night before Tuesday. Give yourself time between now and the weekend to start working on it. All right, other than that, I will see you guys next week. I will stop recording.